Hey everyone, welcome back, and today let's not write some neat code because today's video is going to be a little bit different. I'm going to be going over 5 of the most common dynamic programming patterns, which are very fundamental in learning about dynamic programming and even solving some more difficult and complex dynamic programming problems. And what I'm showing you right now is a Google spreadsheet where I have collected the 5 categories that I'm going to be talking a little bit about today. I have also gathered a few sample problems for each category. You can see the first one that we're going to be going over is the Fibonacci numbers, and I have some sample problems collected. And for most of the problems and categories that I'm going to be going over today, I've actually already made video solutions. So if you want to, watch a video on, let's say, climbing stairs, which falls under the Fibonacci numbers category, you can go ahead and watch that video over here. And if you find these videos helpful, I encourage you to check out my Patreon, where you can consider supporting the channel if you would like to. It's completely optional. You do not have to, but I do want to quickly thank the 21 Patreons that I currently have. Thank you so much for supporting the channel. Now let's continue with the video. So the first pattern that we're going to be going over today is the Fibonacci numbers pattern. So if you are unfamiliar with the Fibonacci numbers, basically the 0th Fibonacci number you can see represented with f is the function name. So f of 0 is 0. That means the 0th Fibonacci number is 0. The first Fibonacci number is 1. And for every Fibonacci number that comes after it, it's basically going to be the summation of the 2 previous Fibonacci numbers. So you can see for every n, for every Fibonacci number greater than or equal to 2, it's just going to be the summation of the 2 previous Fibonacci numbers. So Fibonacci number of 2 is just going to be Fibonacci number of 0 and Fibonacci number of 1 added together, which is just going to be 1 in this case. Now if we continue, so let's say our 0th Fibonacci number is 0, next is 1, next is 1. The next position, we're going to be adding these two numbers together, which is going to be 2. Next, we'll be adding these two numbers, which is going to be 3, etc., etc. So why are the Fibonacci numbers a dynamic programming problem? Why is dynamic programming useful for Fibonacci numbers? Let's say arbitrarily we wanted to get some random Fibonacci number, such as Fibonacci number of 6. Well, how the heck do we compute that? Well, a naive way to compute that is going to be with a decision tree. So the decision tree, as you can see, is going to be a very fundamental part of dynamic programming problems. If we want to compute Fibonacci number of 6, as per the equation I just mentioned a second ago, we can get that by computing Fibonacci number of 5, adding it with Fibonacci number of 4, right? To get a Fibonacci number, we can take the 2 previous Fibonacci numbers. And of course, we're going to keep continuing this entire decision tree until we get to the base case where everything in our tree is either Fibonacci number of 0, which is a base case that evaluates to 0, or Fibonacci number of 1, which is also a base case which evaluates to 1. So you can see that this tree is going to get pretty large. But you can also kind of start to see there is some repeated work going on, which is the reason why we can apply dynamic programming. You can see that we're trying to calculate the 4th Fibonacci number over here, right? So suppose we did calculate it, then we finish this left portion of the tree, then on this right portion of the tree, the entire tree itself, the goal of this tree is just to compute this 4th Fibonacci number again. So why are we doing the same thing twice? So that kind of leads us to go in a different direction with dynamic programming. So if we want to compute the 6th Fibonacci number, we can just go ahead and compute the 5th Fibonacci number, right? And when, as we are computing the 5th Fibonacci number, the 5th Fibonacci number wants to compute the 4th Fibonacci number, right? So we're going to keep going like this. So as we compute the Fibonacci numbers required to compute this Fibonacci number, we're going to end up computing all of these, right? Of course, these are our base cases, right? The 1st and 0th Fibonacci numbers are our base case, right? And if we want to compute this, we're going to need to add these together and add these 2 previous numbers together. To compute this one, we're going to need to add these 2 together. To compute this one, we're going to need to add these 2 together, etc., right? How about instead of starting at the top, we start at the bottom, meaning we start at the 0th Fibonacci or at the beginning, right? Basically, this is called the bottom, and what I'm showing you is the bottom-up dynamic programming approach. So we're doing the bottom-up approach, but one thing I want to mention, this Fibonacci numbers pattern is a one-dimensional dynamic programming problem. So, you can see that we just have a single array of size n. This is one-dimensional. That's where the Fibonacci numbers dynamic programming pattern falls into, and there are many problems that do fall into this pattern. I've listed some of them in the spreadsheets. One of the problems is climbing stairs, which is pretty much exactly this Fibonacci numbers problem. And I think that video, I've made a video on the climbing stairs dynamic programming problem. I think that will give you a very in-depth explanation of this style of problem. I'm just quickly going over a little bit about this pattern right now, but I recommend watching those in-depth videos if you want to get a more deeper understanding. But with the bottom-up approach, instead of starting at Fibonacci number of 6, how about we start over here? These two are already computed. If we want to compute the second Fibonacci number, we just take these two, add them together, put them over here, right? If we want to compute the third, we take these two, add them together, put them over here. And we can keep doing that, just like this, until we finally get to the 6th Fibonacci number, right? And one thing you might notice about this particular pattern, right? We're only maintaining, for example, to compute this, we just need to know the 2 previous results, right? To compute this, we just need to know the 2 previous results. So one thing is, even though our dynamic programming, this is a one-dimensional n, size of n problem, we don't actually have to have this entire thing in memory. We can just maintain the last 2 Fibonacci numbers, use these 2 to compute this one, and then we don't have to store this one in memory anymore, right? We only have to store these 2 in memory to compute this next one, and then again, we can remove this from memory, just store these 2 to compute the next one, etc., etc. So that's a little bit about this type of dynamic programming problem. So now let's get into a couple more complex ones. So the next pattern I'm going to be talking about is the 0-1 knapsack pattern. And you can see we have a couple example problems on LeetCode. One of them that I've solved and have a video solution for is the partition equals subset sum problem. So the 0-1 knapsack problem, the name comes from, this whole 0-1 comes from, so we're given some, quantity of things available to us. In this example, let's say we're given some coins, and we want to use these coins to sum to some particular target. In this case, we could ask, what's the minimum number of coins required to reach the target? We could ask something like that, but the most simple thing is it possible from using these coins, is it possible for us to ever sum up to this target? That's the most simple question. So that's what I'm going to be talking a little bit about. Now, if you want to get a more in-depth explanation of this pattern, I recommend watching my video explanation for this particular category in the spreadsheet that I linked. But so the 0-1 comes from the fact that from this available set to us, we can use each of these coins either 0 times or we can use it 1 time. We can't use it an infinite number of times. We have a fixed quantity of these coins. We can use each one 0 or 1 times for us to possibly sum up to the target. Now, if for each of these coins we can use it 0 or once, how many different possible combinations could we have with these available coins? Well, for each one, if we can use it or not use it, that's 2 options, right, for each coin. So that's 2 times 2 times 2. Whatever the size of the input array is going to be, the number of ways we could do it is 2 to the power of n. Now that's not very efficient, so how can we use dynamic programming to speed this up? Well, remember, our initial target is 5, so let's ask ourselves, how can we get a sub-problem out of that, right? Because after all, dynamic programming is all about getting sub-problems. Well, if our target is 5, we can use each of these coins once. Let's suppose we start at the sub-problem 5. We want to know if we can sum up to 5. Well, suppose we use the first coin. Then what does our sub-problem become? If we use the first coin 1, our sub-problem is then 4, right? We want to know, can we sum up to 4? Only thing is, we are not allowed to use this first coin anymore. Or let's say we skip the 1, right? Let's say we don't use the 1 at all, then we want to use the coin 2. Then the sub-problem becomes we use the 2, and then we're left with a sum of 3, right? Where we want to target to end, we want our sum to end up being 3. We already used the 2 coin, now we have the 3 coin available to us, right? We skip the first coin. Or another branch is we use that third coin, in which case, we use the third coin, then we have a sum left of 2. That's what we're trying to target up to. So that's kind of how we would get the sub-problem with this 0-1 knapsack, right? When you actually break it down like this, it's not too difficult. Now the question is, we're drawing this brute force decision tree. How can we actually speed it up? Now, this is going to be a little bit more complex than the one-dimensional dynamic programming solution that I showed you. The dimensions of this are going to be a little different, right? Let's think about it. What are the dimensions? We can see that we have some target sum that's going to be available at any given point, right? The biggest it could possibly be is 5 because all our coins are going to be positive, right? We want to know, can we sum up to 5? Every time we add a coin, we're going to be decreasing the target sum to some smaller value. Now, if it ever became negative, like if it became -3, that's invalid, right? That's our base case where we're just going to return false. That's an invalid case. Otherwise, the target could be from anywhere from 5 to 0, right? So that's one dimension of our problem, right? Of our cache or our dynamic programming grid. The size of the target is one dimension. Another dimension is we could use each coin 1 or 0 times, right? So for each coin, we want to know, did we use the coin or not? And actually, one step further than that, at the beginning, we have the entire list of coins available to us. If we use the first coin, then the subproblem becomes, okay, the target is 4, right? And now we don't have the first coin available to us. We only have the first 2 coins. Or if we skip the first coin, right? We skip it, we don't use it, our target remains 5, then we have the last 2 coins available to us. So you can see that this is what the dynamic programming grid for this problem would look like. The dimensions are a little bit more larger, right? This is 2-dimensional. This is more complex than the Fibonacci numbers problem, obviously. But the idea is still similar. We are using the idea of sub-problem. So here you can see we have 2 dimensions, one for all the possible target values we could have, and one for all the possible coins we could use. And this is our base case, right? If we had a target of 0, we return true, right? Because we want to know, can we sum up to the target, right? And every time we use a coin, we're basically subtracting it from the target amount. So if we ever got to a target of 0, we're basically going to return true, right? Because it's always possible to sum up to the target 0. And so ultimately, we want to know what value would go in this position, because this position represents, can we sum up to the target value? And it represents that we are allowed to use all possible coins. This position similarly is also summing up to the target 5, but this position tells us we're only allowed to use the available coins 2 and 3. So here we can use any of the coins. Now, if we want to know if the value in here is true, what positions are we going to go to next? Suppose we use the coin 1. In that case, we're going to be looking what value goes in this square. Why are we looking in this square? Because if we use the coin 1, then the target that we're looking for is then 4, and we go down a notch because then after we use the coin 1, we only have 2 and 3 available to us, which is why we're looking diagonally in this position. If we do not use the coin 1, if we skip the coin 1, then we're just going to look directly below because we still need to sum up to the target 5, but we decided to skip the 1 coin, and then we only want to use 2 and 3, which are also available to us. So this is kind of how the 0-1 knapsack problem works out. There are many variations of this problem, but this is kind of the main idea. Now, the next dynamic programming pattern I want to talk about is very similar to the one that we just went over, the unbounded knapsack. And one problem that I've solved for this category is the coin change problem, a very famous problem. And you can watch that explanation here for a more detailed explanation of this unbounded knapsack category. So the difference between the 0-1 knapsack and the unbounded knapsack is pretty much in the name. This is unbounded. What does that unbounded refer to? It basically means, let's say, these coins that are available to us, instead of choosing each coin 0 times or 1 time, we are allowed to use each coin an infinite number of times, right? That's what unbounded means. But the goal, let's say for this problem at least, is still the same. We still want to sum up to this target value. And I left the grid here because we can actually reuse this exact grid for the unbounded problem as well. So as you can see, the unbounded and 0-1 knapsack problems are very similar if they can be solved with the same grid. This is also a 2-dimensional dynamic programming problem. Now, when we had the 0, 1 knapsack, it was possible to sum up to this target 5, right? If you just take 2 and 3, use each of these values once, we can sum up to target 5. But with the unbounded knapsack, there are multiple ways to do it, right? We can take 1 plus 1 plus 1 plus 2, right? We can do it this way because it's unbounded, right? We can choose this 1 value 3 times and choose the 2 value once. Now, this is obviously a pretty simple example, but there are more complex examples. But what's the difference with this unbounded and the 0, 1? Basically the way that our grid is going to work, right? Let's just go through an example. So similarly in this position, we're asking, can we sum up to the target 5 with all 3 coins available to us? So if we want to know if this value is true, how are we going to decide it? Well, if we decide to use the 1 coin, instead of going diagonally down right, we can go straight to the right. Why are we going in this position? Well, obviously, if we use a 1 coin, then we want to know, can we sum up to the value 4? But we're going to this right position because just because we used a 1 coin doesn't mean we can't use it again, right? So when we're in this position, we can use any of the coins that we want. Now, just because we have an infinite number of 1s doesn't mean we're required to use a 1, right? So we can also go straight down. Because if we go straight down, that means we didn't use a 1 coin, so we still want to sum up to 5. But now we're just going to decide to skip 1, right? We don't have to use it. We're not going to use it. We're just going to use the other 2 coins. So basically, the way the unbounded knapsack is basically, you know, the directions that we're going to look in this 2-dimensional grid, right? So for every point, like if we're trying to get the value that goes here, we can choose to go right or we can choose to go down. And so obviously, you know, the value we're looking for is what goes in this position, because with all 3 possible coins available, we want to know, can we sum up to 5? But the way we would actually compute the values in this grid is bottom up, right? Instead of computing this first, we'd want to start down here because as you can see, you know, any particular value like this one depends on the bottom and depends on the right. So we're going to compute this from the bottom going left, you know, starting at the bottom, going left, and then going up, right? This is called bottom up, because then if we do it in this direction, right, and then we start here, we do all these values. Now, let's say we've computed all of this and all of this. Then when we want to know the value that goes here, we can just look straight down. It'll already be computed down here, or we can look straight to the right. It'll already be computed over here, and then we'll know the answer that goes in this position. And for a more detailed explanation, you can always watch my coin change video. And the next category we're going to be going over is the longest common subsequence category. There are many different dynamic programming problems related to subsequences, and I think LCS, this longest common subsequence problem, is a good start to understand some of these. I've listed 4 down here, but of course there are many others. You can see up here actually this maximum alternating subsequence sum. I put this in the Fibonacci numbers category, but it also falls in this LCS category as well. And you can see down here longest palindromic subsequence, that actually also falls into this 4th category. You can see that these categories, they're not very rigid, right? There's definitely some overlap between the problems. You know, it's hard to categorize this problem, maximum alternating subsequence, whether it's a Fibonacci numbers or a longest common subsequence category. That's why I think kind of understanding these 5 gives you a very good foundation to tackle more complex dynamic programming problems, such as this longest palindromic subsequence, which really takes a lot of knowledge. It takes knowledge from this 5th category and from this 4th category to adequately solve this problem, I think. Right now, let me explain to you a little bit about this longest common subsequence category. I've actually already solved the longest common subsequence problem on this channel, so I'll give a high-level explanation of this category, but basically it has to do with how subsequences work. So for example, if we have a string such as A, B, C, a subsequence of this string is basically a non-contiguous element of the orderings, right? It's basically the similar idea that we did with the coin change problem. For each character, we can choose whether we want to include this character or not in the subsequence. The order does matter. So for example, if we decide to include this A, we don't want to include the B, but we do want to include the C, the order matters. So if we got a subsequence like this, we have a subsequence of A, C, right? We have to put them in this order because that's the order that the characters occurred in the original. And so the main idea of this type of problem is basically if you want to know, all the subsequences for a string like this, we could get all the subsequence for the substring or the remaining portion of the string, not including the A, right? We could get all subsequences like this. And then, once we've done all of that, that's like our subproblem. Then we want to get to the A. And once we get to the A for any of the subsequences over here, we could decide, okay, can we include the A or not include the A, right? That's a 0-1 decision, similar to the knapsack problem. But the longest common subsequence actually refers to taking two different strings. So for example, if we had ABC and the string ace, then we want to know what's the longest common subsequence between these two strings. And the way that's going to work is we're going to compare character by character. We're going to start at the beginning. We're going to see, okay, if these characters are equal. If they are equal, that's good, right? Then the subproblem becomes, okay, we saw that, these two characters were equal. Now we're going to compare the remaining portion of the strings, right? We're going to find the longest common subsequence between these two. That's what the subproblem is going to be in this type of category. But if the characters are not equal, so in this case, we can see BC and CE, the first characters in this case, B and C, are not equal. So then what's the subproblem going to be in that case? Well, we're going to have two different subproblems in that case, right? Since the first characters are not equal, we're going to have a branch. We're going to have two decisions. We're either going to find the longest common subsequence. We're basically going to skip the B character, right? We're going to decide to just skip it, in which case we would want to find the longest common subsequence between these two strings, C and CE, or we would decide to skip this character, this C, in which case we'd want to find the LCS between BC and between E. So that's kind of how it would work. And as you can see, we could potentially split in every single case. Now, since this is going to be a two-dimensional dynamic programming problem, what is the grid going to look like for this problem? Well, as you can see, this is also going to be a two-dimensional dynamic programming problem. We could compare any position of the first string ABC to any position of the second string ace, right? So we're just going to take the dimensions of the two strings and multiply them together to get this grid. Now, as you can see, the base cases are going to be, well, the good base case is going to be if we reached the end of string 2, right? The end of this string, and we reached the end of this string, in which case we'll just return 0, right? What's the longest common subsequence between empty strings? It's just going to be an empty string itself, right? Now, what if we reached any of these X's? Basically, we're asking what's the LCS between a string like E and an empty string, right? There is no longest common subsequence, so this is a wrong base case. Similarly to this position, a C and an empty string, that's also not a valid base case. Now, so how are we going to actually compute? So this target value is what we're looking for. This top left corner, that's what we're looking for, similarly to the other two-dimensional problems that we went over, right? So you might be noticing a pattern. This top left corner is usually the target value we're looking for because we're comparing the beginning of ace to the beginning of ABC, right? We want to know what's the LCS between the entire strings. Now, in this case, since A is equal to A, where are we going to be going? Well, in that case, we want to compare CE to BC, right? So in that case, we're going to be going diagonally down right. We don't have to go here and we don't have to go here. We just have to go diagonally, right? Now we're comparing C with B. These are not equal, right? So we can't go diagonal. When they're not equal, then we want to know, okay, what's the LCS between CE and C? In that case, we go right. Or we want to know what's the LCS between BC and this string, just E, right? We're not looking at this character anymore. In that case, we want to go down. So you can see for any particular position, any position in the grid, we're either going to be going diagonal or we're going to be going down and we're going to be going right. So in this case, similarly to the other one, if we want to know the value that goes in the top left corner, it might be helpful, it might be beneficial to start at the bottom right, keep going, keep going, keep going, keep going, and then finally, once we've done all of these, it'll be easy to compute this value because either we're going to be going diagonally, in which case we'll already have that computed, or we'll be going to the right and we'll be going bottom, which will already have those values computed as well. So this is also the bottom-up approach, a two-dimensional dynamic programming problem. Okay, so the last category that I'm going to be going over today is the Palindromes dynamic programming category. As you might know, though, there are definitely categories that fall outside of these. There are definitely problems that don't fit in nicely to any of these 5 categories that I mentioned. Of course, there are many types of dynamic programming problems out there. And as you can tell, some of the problems I've even listed happen to actually fall into multiple categories. This LPS problem falls into category 5 and category 4. This problem up here falls into category 1 and category 4. So I'd highly encourage you to, list out some more categories that you'd like me to go over in the future in the comments if you'd like. Now, there are many things I could talk about when talking about palindromes, but what I'm going to mainly focus on is how palindromes relate to dynamic programming, and specifically, I'm going to be showing you a little trick with palindromes that happens to be required to solve a lot of these types of problems efficiently. So suppose we're given a string like this one. How can we use dynamic programming to our advantage to maybe count all of the palindromes in this entire string? Well, let's think about it. So a naive way would be something like this. Let's say we ended up getting to this entire string. We want to know, is this string a palindrome or not, right? We start at the beginning and we start at the end, compare character by character. Now these two characters are not equal, so we know that it's not a palindrome. But in the worst case, we would have to compare character by character and basically looking at the entire length of the string, right? So that's the worst case. We'd have to go through the entire string to know if it's a palindrome, right? Now, let's say we want to know, okay, we're not looking at this anymore. We want to look at the entire string, right? We add this character to our consideration. We're asking, is this entire string a palindrome? So once again, we would have to start at the beginning, start at the end, compare character by character. In this case, they are equal, so we'd keep going. Compare character by character, and basically what I'm getting at is we would have to look through the entire string once again, right? That entire length n for every single substring that we're looking at. So even if we just looked at this entire string, if we add just one more character, then we have to look through the entire string again because of how basically the nature of palindromes, how they work. Is there any way that we could cut down on this type of repeated work? Well, there happens to be one way. Basically, we would have to change the way that we build upon our strings. Instead of looking at a string and then adding a character to the end of it, how about we start at any given string of size 1 and then expand outwards. For example, if we were looking at a string like this one, it's just a string of length 1, so we know it's a palindrome. Now, if we want to look at a longer string, let's say we want to add one character to the left and one character to the right, how do we know if this new string is a palindrome? Are we going to start at the middle and then start expanding outward again? No, because we already know this middle portion happens to be a palindrome. All we have to do is now compare the new left character and the new right character. They happen to be equal, so we know that this new string is also a palindrome. We did that in an O of 1 operation. It makes sense when you look at a small string, but even for a big string, it would work the same, right? If we knew already that this string is a palindrome, this big string, if we just add the left character and add the right character, we already know this is a palindrome. So if we add a new character to the left, a new character to the right, now we can check in O of 1 in constant time that this new string is also a palindrome, because we only have to compare this new left character and this new right character. Now, one detail to mention is the way I showed you is only going to get us odd length palindromes, right? Because we start with 1 and we keep adding 2 characters, so we're always going to have odd length palindromes. If you do want to check even length palindromes, you can do the same. You can just start with 2 characters like this. Are they equal? E and C are not equal. So of course, since these are not equal, if we expand outward to the left and right, none of the new strings are going to be palindromes either. So we don't even have to check those. So that's kind of the main idea that I wanted to go over with palindromes. It might seem pretty simple. Once you know it, it actually is pretty simple, but you would be surprised how many problems require this particular trick that I just showed you to be able to solve them efficiently. I have at least 3 of them listed in that spreadsheet, and I'm sure there are many more. So I hope you found this video helpful. If you did, please like and subscribe. And if you do want to take a look at these problems, this spreadsheet will be linked in the description. I do have solutions for most of the problems that I listed, and I do have a problem link for pretty much all of these problems. If you find any more on LeetCode that you feel fit into any of these categories, feel free to suggest them in the comments. I'm sure many people, including myself, would find that helpful. And if you enjoyed this new style of video, please let me know. And if you have any suggestions for future types of videos, also please leave that in the comments below. I enjoyed making this video. I hope you all found it helpful. Thanks for watching, and I hope to see you again soon.